We all on track to get in proposals? The projects? Yeah? Some of you have turned them in already, which is great. Okay, well, due tomorrow by the end of the day. Just one extra credit point given for getting it in on time. So,
but there's only like 100 points in this whole class, so just one extra credit point is like 1%.
Yeah, it counts for a lot. Okay, so we're going to continue today with our look into generative convolutional neural networks. Last time we looked at these models that look a little bit more like the things that we were studying when we were looking at recurrent neural networks. Now we're going to start to look at quite different things. And today we'll be talking about what are called variational AutoEncoders. Fancy big name. You often see it, read it, VAE. And, you know, some fun math in this. At least I think that. But having a PhD in math, I think most math is fun. So, well, you can decide at the end of this if this is fun or not. Okay, so remember what we were doing last time? Is that we were wanting to be able to, you know, estimate this likelihood function, right? This data generation function. This is about this p theta of x's, right? So p is this likelihood, this probability being assigned to x, a data sample. Theta represents the fact this is parameterized. This is a parameterized function. This is in this class. This is always a neural network of some kind. And the way that we did this was we made this autoregressive. We took the full distribution and we factorized it. Use this what's called the general probability into this product of likelihood functions where they were all conditioned on like the previous pixels in this case. So you pick some ordering, and then you can write this down. And you know this is a tractable probability function. I mean it's kind of ugly, but you know it's something that can be learned, as we saw last time. Where we're going next is to again think about how to estimate this this likelihood function for the data, but this time we're going to set up the problem in this way where we think of this as like having marginalized a conditional distribution conditioned on some variable z that we have yet defined. Together with some prior distribution for that variable z, the marginalizing means that we're gonna integrate over that variable, integrate it out. Okay, so at first glance, like this doesn't seem like this is going to be very helpful. We're just making it more complicated, and indeed things become quite complicated, like mathematically. However, this is definitely a worthwhile direction to go, in that this z here is going to be some kind of what we'll call latent representation or latent factors that generate our data point x. Okay, and this becomes really useful. Remember, we were talking about things like dimension reduction, being able to kind of represent your data in its like essential kind of form. We often call these factors, or something. The inputs, like the essential inputs that go into describing, or we often think of this as like being able to generate the data point itself. So this kind of gives us a way into doing that mathematically, and this is how this is the area we're going to explore today. The issue here is is this integral. So it's like most of today, after we describe what autoencoders are, and then add the variational part, most of today is going to be figuring out how do we deal with the fact that we've got an integral here. This sort of complicates things. Well, this very much complicates things. This talks about what we're going to do is derive a lower bound for this likelihood, and you'll see what I'm doing here in a second. Okay, so just some background first. Autoencoders. So what are autoencoders? So we've talked about encoders. We've used that word at least a bunch of times. This is just a term that we use when we have we have a function that takes us from usually like our data to some representation of that data. We think of it as like encoding that data. And Z being, we've usually called it something like the embedding or a representation. Sometimes it can even be called the code, associated with this data point. So this is just some mapping from our input space to some other space, usually lower dimensional. And autoencoders, the auto part of this is auto, think of it in this sense as being self, like we talked about self-supervised learning last time. We're going to be using the data itself as a way of learning how to do this encoding. This is what we're going to look at next. These encoders, these are neural networks usually for us. Here's a short history lesson of what they've been for convolutional networks. Obviously, we're using convolutional layers and ranges and things like that when we're dealing with images and any encoding at all. These days that seems to be state of the art. Again, Z, these features, this embedding, this representation, this code is usually small. Usually small. And why small? Why would we want to reduce the dimension of the input? Why not make it bigger, for instance? What's the thinking there?
You can use it for compression.
Okay, so it's like, and in that sense, it's like really clear the connection to how we're going to train these things, because what we're going to try to do is from these features, try to recreate the data itself, right? So the key in compression, right, is that you try to find some appropriate representation of that is compressed, that's smaller, in the like in a logical sense, and then but it has enough information to like essentially recreate, or mostly recreate, where that came from. So we were just saying something about this in lead up to this slide, but what we really want is we want these features to capture meaningful factors of variation. So again, like in a kind of pure sense, what we hope that these things are this might be, think of this as an image, right? So there's a lot of features. It's in a very, very high dimensional space. We hope that whatever this is, it's much, much lower dimensional, and it represents the essential variation that you're seeing in the input data, right? So for like MNIST, just these digits from 0 to 9, essential features there are things like, which number is it, and what's the style of that number. So where do the curves go when you're writing a 9 or an 8? The variation between a 9 and an 8 is they kind of share something in common in the top part, but the bottom part of the number is different, right? And so these are all ways in which that data varies, and you want these features to somehow capture that in a very in the most minimal way possible. I mean, what the actual minimal dimension is something somewhat difficult, pretty difficult, given an arbitrary data set to figure out, and is related to some old and deep ideas in machine learning, statistical learning itself. But again, the idea is whatever this thing is in our data set, we want this to just represent enough information to be able to reconstruct it. Removes a lot of the redundancies and captures a lot of the like shared features of our data set. It's easiest to think about that MNIST. When you start to go to other data sets like CFAR, ImageNet, whatever, like, you know, it becomes, you know, less and less clear how to describe what all the factors are. But again, you know, there's certain classes of objects. They're oriented in certain ways. They have certain colors. They come in with certain backgrounds. You know, whatever the variation is there, you want that to describe it. And then how do we learn this? Well, this is the auto part. Is again, we're just going to have another function. Again, another like neural network here that's going to go from this encoding, this representation, and it's going to go. You know, if this was an image, it takes this, you know, this image tensor, compresses it down into a vector of length n, and then from that vector of length n, it needs to kind of recreate this tensor. And so you call this a decoder, right? Like this encoding took you from the input to a code, and the decoder takes you from the code back to like the input or something close to the input. And you know, we have a good autoencoder if the reconstructed input data is in some sense close to, you know, looks like is similar to the original input data. So how do we measure that? Right, sorry, real quick. What do these things look like? Yeah, if, you know, modern convolutional networks, these are going to be, you know, convolutional layers, radius, things like that. These are going to be, again, convolutional layers, but they're going to be, you know, transpose convolutions. Again, you know, using things like radius as activation functions. But the way that we train these things is we literally, you know, take the original data, run it through this model, and compare it to, you know, what this output is, which is this exactly. So this is something like, you know, using some notion of, you know, these are tensors. You can always take a tensor and like make it into one long vector. This is some notion of comparing the whole, you know, the whole list of entries here and here. So, you know, often you will see things like a Euclidean type distance, or a Frobenius norm, which is like more appropriate for things of higher orders. It's just the same idea, it's entry wise. You know, comparing the differences between entry, you know, the differences between entries, you know, entry by entry, and somehow aggregating all those together. This could be L1. These are very common, you know, very common functions you would use, or distance metrics you would use to, you know, to compare to calculate how similar they are. And of course, you know, this becomes a zero. This isn't really truly like a metric. This becomes zero when the two are equal, if and only if the two are equal. So by doing gradient descent on a function like this, you know, the smaller that loss is, the closer our reconstructed input is to our original input, right? So that's how we treat these things.
Is there any regularization?
Sure, yeah, this is everything we've learned so far you can do.
So what would regularization mean in this case?
Exactly what it means in other cases. I mean, like, depends on what regularization you're talking about, but like, if you're going to do like an L2 regularization, you know, this is like, it's exactly the same like bias you're trying to build into the features, which is like, I don't want my parameters to be too large, because that usually represents like having overfit to the data itself. And if I want this to kind of, you know, generalize outside of my training set, that usually helps to do that to some degree, right? If it's too strong, you don't learn anything. All the same kind of things, and you know, apply.
How about dropout?
Yeah, all the same things apply. It would be like, you know, that you know, again, would be give you this kind of ensemble idea of having, you know, learned many ways of representing this, and this being some kind of like, you know, average output of all of that, and then, you know, reconstruct it from there.
Yeah. So is this a sequence to sequence?
Sequence to sequence? No, not sequence to sequence. Think of this as an image. Some encoder. So like, think about having done the classification problem, you know, getting down to the fully connected layers, but like not being supervised in that way. Once you get on the fully connected layers, now you kind of flip this thing on its head and do a bunch of transpose convolutions until you get back to a tensor of the same size as the input, and then you supervise it by saying, this has to be the same as that. So not sequence to sequence. It's just simply, compress this, and then expand it again, and do that in such a way that everything that we learned, like the encoder and the decoder we learned here, do a good job of reconstructing the original data from the compressed representation.
So essentially there is no encoder here. We can take any layer's output and assume it to be encoded because there is no concrete split as a sequence.
Yeah, I guess so. I mean, that would sort of defeat the point of like having this like gradually reduce the dimension of your input and then reconstruct it again. You typically think of this as having like an hourglass kind of shape, right? And the smallest dimension is the code that you're focusing on. You want that thing to to be your representation. But it's true, like you could use any aspect of it. Yeah.
How about shortcuts? Are we going to do anything like ResNet?
Yeah, I mean these decoders could be ResNets. I mean,
but it could be kind of dangerous because we could just make all the main ones just 0 and then just use a shortcut, and it'd be perfect.
No, you can't, right? Because this is a smaller dimension.
Oh.
So, like with ResNet, right? Every once in a while, you're going to reduce the spatial dimensions, right? So, like that's the point, right? It's like you do that a bunch of times until you get down to something small, and then you can go backwards. So, yeah. Like if this is the same size as this is an identity function. Right? You're not learning anything. The whole point of this is saying compress all the information, all the relevant information needed to reconstruct this image, in n dimensions to this representation. That's really what it is. So if you're not doing that, then this is like there's like sort of no point in what you're doing.
So can I say this is something similar to the video compression algorithms that YouTube uses? I saw like kind of video compression that WhatsApp does.
Is this similar to like video
compression?
I mean, yeah, these could be videos. I keep talking about images, but this is really general, right? This could be video, so it could be instead of a 3-way tensor, it could be a 4-way tensor, so it has the additional like dimension of the sequence, and then you can compress that down and then decode it back to a 4-way tensor. I mean, everything here is very general.
So if that's the case, then like could you think of like Z as like a JPEG, and then you're going from an image to like something like a JPEG and then back up again?
Yeah, but
so in that case, are we just learning like a bunch of fast Fourier transforms?
I mean, the inductive bias here. I mean, the answer is no. The inductive bias here won't learn won't learn a Fourier transform. Although there's definitely work along these lines in doing that, which is actually there's some very cool stuff there. But in general, no, that's not what you're doing. This is a neural network. It's a sequence of linear transformations with nonlinear activations in between, and that's not the same as. It's not likely to learn a Fourier transform unless you build that into the inductive bias.
I just wanted to clarify something. So this input data, this could be like more than one image at a time, or are we doing this like one image at a time?
Yeah, one image at a time.
So the loss.
Or like just real quick, in the video case, this could be multiple frames, which represent like a certain like number of seconds of video, and that would be you could think of it as multiple images that are correlated.
I guess I'm just wanting to know, like, does this loss function involve a single image? Do you like?
Yeah, I mean, like whatever this is, it's a single data sample. So like whatever your data set is. So if your data set is CFAR, these are CFAR. This is a CFAR image. If it's video snippets, it's a video. If it's language, it can all like this could all. I mean, think like we've seen this before, right? Like our transformers encode, our input and then decode it back to, to the original sequence, or you could do seek to seek in this case. But you can't do that there. Here, this is simply something like, you have a kind of continuous representation of your input, and you're going to try to reconstruct it through, after compressing it. And compressing here is simply in terms of dimension.
I guess like maybe why I'm a little confused is I guess I'm just like used to seeing loss functions that are like sums of
Sure. So like this is for one example, and so for your mini batch is going to have, you know, whatever, 64 of these, and so that's going to be a sum of 64 of those kinds of, like, you know, those terms.
So the back propagation you would
Or
do,
an average of all those, I should say, but yeah.
like if you were trying to learn like your encoder or decoder, so you would do the back propagation based on like the sum of those lines?
Yeah.
Okay.
Yeah, I mean, exactly the same way that we do for every, you know, everything we've done so far. Just every single one of those terms in that sum, you want to minimize, right? So like gradient descent is going to work to minimize that whole sum or that average. Essentially equivalent, just, you know, some slight detail there, but yeah, that's right. This is like, so think of this as like when we're doing classification loss, this is like a single, you know, negative log likelihood term, right? Where we're comparing our one hot encoding for the correct class with our like probability distribution over all the classes. Right? And in a mini batch, you're going to have many of those, and you're going to average those, and that's going to be the gradient that's going to be the function you compute the gradient of. Same thing here, just sums of all those things, compute the gradient of the whole thing. Yeah. Importantly, this is unsupervised in the sense that there's not a label here. We use the data itself as the label. So it's really, you know, in current parlance, self-supervised, but I'll keep pointing that out, that both terms kind of mean the same thing here.
So is this a regression then?
Yeah, this is a regression problem, exactly. Yep. There's actually quantized autoencoders, which are something in between, but we're not talking about that here. This is a regression problem. When you have like an L2 loss, that's a regression. Or an L anything loss is a regression. Okay, so what are these good for? This says throw away the decoder. Actually, the decoder is like the most fun part of this, is that you can actually like create, you know, you can create samples from your distribution by sampling from this space and then applying the decoder. But you know, if your whole job here is to create a, you know, a compressed representation of your data, then all you need is the encoder to do that. So you know, you need both to do the training, but the point is that, you know, when you're done, you have an encoder, you have a decoder. You can use both for what they're good for. All right, we need to keep rolling here. All right, so variational autoencoders. So there was nothing probabilistic at all about an autoencoder, right? It was you have your input, you have this L2 loss, you're just minimizing, you know, minimizing the difference between your reconstructed input and the input itself. Nothing probabilistic about that at all. So remember, this whole thing started with we want to do generative models here, so we need some notions of probability. And variational autoencoders are doing that for us. They're putting this probabilistic spin on autoencoders. It's going to allow us to sample data in a proper, like, probabilistic way. And you know, our integrals are going to show up again real soon. Okay, so what do we mean by all that? Here's our decoder from an autoencoder. Right, we have our Z's, our features or our representations. We're now going to start using another name for this. We're going to sometimes call these our latent factors. Latent here means hidden or like unobserved. Okay, so we observe the image. We don't observe the the factors that actually generate that image. So that's why it's sometimes called latent. And then we have the reconstructed or the data, the sample that is generated by that by those latent factors. So adding some probabilistic notions here, we'll think of this latent space as having its own distribution, over it. So there's going to be, we'll think of this as a prior. If you've done some, Bayesian statistics or probability, some of these words will make sense. If not, it's totally fine. But we'll talk about this often as a prior. So it's something that we kind of already believe, like some distribution we already believe that this data should follow, or we just, and as you'll see here, we're just going to decide what it is, make it simple so it fits kind of our notions of what we want our latent space to look like. And from that, we are going to have, a conditional probability. And we've seen these before when we talked about this like in classification, right? We, condition on whatever point we sample from here, there's some probability that we now sample a data point given that. That's what this distribution represents right here. So this is like, this is for sampling from the space here, and this is for sampling, given the sample from here, sampling which data point we get from the data space. Okay? So that's really going to be our, this is how we're going to build in probability to the ideas. Remember, we saw this already when we saw these integrals, so here's where they come back. Yeah, sorry, I should have had that slide up already. We're trying to estimate the parameters for this generative model. How do we do this? Again, we're gonna maximize the likelihood, which is going to be the integral of these two things multiplied together, integral over z, so integral over this space. But we're gonna have to give some sort of definition to these distributions. And so, how do we do this? Well, this is what we're trying to learn. Like this relationship is the thing that we're going to try to learn from the data. So this is the thing that's going to be a neural network. I guess it'll be next on the slide. But we need to make a choice here with respect to like this prior, this distribution over this latent space, this set of features. So how should we represent such a prior? Well, one thing it's saying here is pick something simple, like a Gaussian. Actually, it should say something stronger than that, like an isotropic Gaussian. Who knows what an isotropic Gaussian is? Actually, forget about it being isotropic. How about just like having the what would it mean if the covariance matrix for your Gaussian is diagonal, for instance? What does that say about the features?
They're diagonals, right?
Yeah, so the covariance matrix is diagonal.
So in that case,
So all the what's in the covariance matrix? What's on the diagonal?
in that case, it's either like super independent or super like anti-independent.
Yeah. Right. So if you're so in the covariance matrix, you're basically computing all the covariances of of one feature with another. Along the diagonal, you're getting the feature with itself. So that's actually variance. Okay. And then everything else is a is a covariance of one feature with a different feature. So if you have a diagonal matrix, then all of your covariances are 0 for every pair of features.
Oh, so isn't covariances when you divide it by something, it turns into the correlation? So that means it's not correlated at all.
Yeah, right. I mean, yeah, that is a way to think about it. Yeah, that these aren't correlated. So like,
Then they're independent. Then.
yeah, they're not truly independent because we're only considering the statistics up to second order. But in a Gaussian, that does imply independence of the features. Gaussians are determined by the first and second moments, and so you can read off independence from there. So why does this make things simple? Well, first of all, Gaussians are super easy just to work with generally. Like they make math, and you can actually do integrals and stuff with them really nice. So we would pick Gaussians. But also, if we pick Gaussians with that have diagonal covariance matrices, or even stronger, that they're isotropic, meaning that the variances on the diagonal are all the same, then we have an even stronger assumption that each of the factors here is independent of another one. And actually that makes a lot of sense for what we're trying to do here, right? What we're trying to do is we're trying to take all, like, whatever information is up here and compress it into factors that, like, best, you know, like in a minimal way, you know, allow us to reconstruct the data itself. So we would hope that these things are independent, because if they're not independent, that means some of the factors are sharing information, and that means that, like, this is not minimal, right? In some sense, like, we should be able to say, like, make it even smaller if they are sharing information. So if we enforce that whatever this ends up being, that this has to follow a very simple, you know, diagonal, or Gaussian with a diagonal covariance matrix, then we have really, like, you know, latent features that are sort of behaving the way that we hope they are.
So couldn't we just eigenize it? Use an eigen?
Yeah, no, I mean, yes, you can do those kinds of things, but we're gonna assume this. Remember, like, we get to choose the form of this distribution here. So we're just gonna make it very simple. We're gonna make it a Gaussian with this diagonal covariance matrix.
Professor, could you clarify what is the firm I?
Yeah, that corresponds to the actual sample that the ith sample in the batch.
Oh, okay.
It's there because we're going to see it kind of come up again.
But you said you represent that distribution as a neural network, right? So
Right.
it's deterministic, right? So that.
Yes, that's a great point. Okay, so anyways, we spent a lot of time there, but we get to choose what this is, and we're going to choose it to be something simple that has some, you know, that has some of the things that we expect from the space, like we expect the features to be independent of each other. Now, for the decoder part, it's going to be a network. This mapping from the features to the data space is probably very complex. Right? We're generating this image from these features, so that needs to be a neural network. But it's exactly what you said. Neural networks up to this point, like what we've done, they've been deterministic. They're not really like the notion of, like, probability in them as we, like, forward, you know, the input through the network. So we do need to deal with that. Do you have any thoughts on how you might do that?
Sorry, I don't. I just got the
Yeah, no, that's great. That's awesome. Great. That's what we're going to talk about. All right. So in 1 second, we're going to get to that. How are we going to train this model? Well, this is like the crux of the math problem here. So what we're going to do, now that we have, you know, we made some decision about the prior being this kind of simple Gaussian, and this being some neural network. Remember, what we're trying to do is we're trying to maximize the likelihood of our data. So we want to maximize this. For our training data, we want to maximize the likelihood here. And we bring these two notions together in this integral. But the integral is the problem, right? So our z's in there, our z's built in, but the integral is the problem. Like, in general, like, unless this is a very, very simple, like, linear neural network, we're not going to be able to do that integral.
How is it intractable?
Have you spent any time doing multivariable calculus? Most integrals are intractable.
Yeah.
Like, it's a trick that they play on you when you take your, like, third semester math class. Right? It's like, you're learning all these like great formula and stuff to be able to, like,
cheat and use
so, like, integrate things. But the trouble is that really, for most things you want to integrate, unless you made some really, like, good decisions about what the forms of those functions are, you're not going to.
Or can we cheat and use some kind of numerical method that gets us close enough?
Yep, and that's what our algorithm is going to, like, address. We're not going to be able to do exactly that, and we'll go why. We'll talk a little bit about why, but we'll have something else that will be, an approximation to this interval. Okay, so some of us would maybe just give up at this point and say, well, there's no point in this. I don't know. We'll go figure this out. But I don't blame you. No one wants to do integrals like this. But not Kingma and Welling. No. They show us how to approach this. and how to get really great results. So summarizing, we want to do this. We want to compute this integral. We have a simple Gaussian. Usually that's good in an integral because if, say, like the other distribution is a Gaussian, you could do this integral. Products of Gaussians will have a Gaussian-like there'll be like a Gaussian-like density, and we can integrate Gaussians. So that would be great, but we chose this to be a neural network because we know that this is supposed to be like a really complex nonlinear relationship that takes us from the factors to the data. So how do we do this? Well, we might at first think, well, maybe we can just get by and just compute the posterior distribution here, and from there, work out what our p of x is. But that's just pushing things. There's like a law here. It's like conservation of complexity, and just by kind of moving things around, arithmetically, you're not changing anything. So that's not going to work. So what we end up doing, this is the variational part. The word variational here refers to kind of a whole family of approaches to working in probabilistic settings like this, where you actually estimate one of the things that you are wanting to calculate with another function, and sort of separate them in this way that allows you to then do some calculation and enforcing that thing is close to the thing that you want, and everything works out. So in this case, what we're going to do is we are going to this is the thing up here. This is our network, making things difficult. What we actually, so remember, this is our decoder, right? It's going from the latents to our data space. What we're going to do actually is just this doesn't feel at first like this is going to help, but it does. We're going to actually have an encoder network that takes us from our data to the latents. That actually approximates this likelihood here. So we can't compute this directly because of the intractability of this term, which is already up there. But we can pretend like we know what it is and see how much progress we can make. So we estimate it with totally different parameters than the theta used for our likelihood in the data likelihood in the first line there. So what this allows us to do now is sort of separate these things, like mathematically, again, enforce in the end that these come together, and this allows us to just push terms around in a way that gives us a way to train these things. Okay, so coming back to the question that you had here about the fact that these are not these are deterministic usually. What we're going to do actually is instead of learning for either one of these, this is our decoder network that we've been talking about. This is the new one that we just introduced, the encoder network. The output of these networks, instead of them actually being like, in this case, z directly, or in this case, x directly, they're gonna output the parameters of a distribution that we're going to sample from. So we're going to again use Gaussians. So we're going to output the mean and the covariance matrix of the Gaussian for both of these networks. And then we're going to sample from that. Now, we're not going to enforce in this case that this covariance matrix in either one has any sort of special structure. We're going to allow ourselves to learn that. But we're going to learn the parameters of a distribution, and then we're going to sample from those. There's a looming problem there, in that sampling is not a differentiable operation. So we're not going to be able to backpropagate through this as is. But it turns out there's one more trick we're going to do here that allows us to do that. So building up tricks as we go. So hold on tight, because if it feels like confusing right now, that's fine. It probably is confusing, but these are the ideas, and we're going to put them all together here real soon. Right, sampling from these. Oh yeah, it's worth noting that these sometimes have other names that you would see in the literature and the variational literature. This network right here is something like a recognition or inference network, and the decoder network is a generation or generative network. Okay, so how do we bring this all together to actually like have a loss function that we want to learn, that we can learn from? Okay, well, remember the goal from the very beginning is to maximize this data likelihood function. It's the p theta of x. Right, that's this integral. Okay. We typically don't we don't optimize the likelihood directly. We usually optimize the log of the likelihood. So we take a log here. And now we're going to sort of just do a bunch of math here, and I'll try to motivate each of the steps here and what's going on. But this is going to get us to a point where we're going to have a loss function that we're going to optimize. So the very first thing we do is like, tricky math stuff. Is what we're going to do is we're going to write this log p as this expectation of log p, where the expectation is over z, our latent variable z. Notice that p doesn't depend on z at all, so this is just a constant with respect to that distribution q, that encoder distribution q. So you factor the constant out. This is just an expectation of 1, which is 1. Right? The integrals of our distributions are always 1, and we've like mysteriously introduced q, this encoder network, and this like this auxiliary thing that we just thought would be useful. We introduced it in step 1 here into our calculation. So the first step is like very basic expectation of a constant. It's just the constant itself. Okay, how does this help with anything? Yeah, this is going to come in handy later. Okay, so the next thing we do is we express that likelihood, the data likelihood, in this ratio of conditionals and priors using Bayes' formula, Bayes' rule. Okay, so hopefully you've seen this before, but this is saying something like the following: p of x, or so like p of z given x times p of x is the same as p of x given z times p of z. Right. So both of those are equal to the joint distribution between p of x and z. So if you were to like multiply this times that up there, you'd have that equality. P of z of x times that p of x is equal to p of x of z times p of z. So just again, mysteriously kind of introducing more distributions where certainly this couldn't be of any help. Notice though what we have done in doing this is that we have introduced z into this expectation. So now all of a sudden instead of this being a constant, I mean, it still is a constant with respect to z, but z is now in here. Okay, how's that going to help at all? Well, now we need more mysterious math stuff, and we multiply by this. We multiply by 1 here, so just this constant. How could this in any way be useful? See how that's just 1, so we haven't changed anything yet. Okay, so now we start to sort of break this up using the property of logs, right? Just how the multiplication and division within the argument of a log is the same as like addition and subtraction of the logs of those arguments. So what have we done here? Well, we have a bunch of things. So one thing that we did was this first term here is just the log that's right here. Okay? This is log of this decoder here. This is one of our neural networks. Again, the Z is coming from our encoder network, the other network Q. Okay, what about these terms here?
It's an approximation of.
Well, this is before we say something about what it is, like where did this come from? Well, this is this term and this term here, but this term, we took the thing in the denominator and we put it up in the numerator. Took the thing in the numerator, put it in the denominator. That's why there's a negative sign right here, right? Like we flip those over, just properties of logs. Okay, so that leaves these things right here, and that's exactly what we have over here. And that the plus sign is we haven't like swapped anything over numerators or denominators. We have Q of theta and Q of phi and P of theta.
So that's going to be approximately 1, and log of 1 is 0, so that goes away?
Well, yeah, like this is, each of these terms now have a meaning. It has a meaning. And you were trying to point out something here. This is a term that we hope will make these two things equal, right? This Q of phi is the thing that approximates P of theta, and we do want these things to be equal. So and when we optimize, we'll want to pay attention to that. But let's keep going. So we started off with something kind of really simple looking, and we made it really quite complex. But each of these things have a meaning, and we're starting to get at this. So let's keep going here. We'll get some explanations. Okay, first of all, each of these things here is actually a KL divergence. Remember the KL divergence? We've looked at this at some point in the past.
The KL difference? Was this in KNN? No, that was
no. So we did KL divergence when we were doing cross entropy. Yeah, exactly. And so these are KL divergences because these are integrals where the Z is distributed, as Q. So really what this is, I wish I did actually, but there's like this. If I were to sort of like expand what this notation means right here, there's an integral now over Z, and I put the function Q theta in there, right? That's this probability distribution. Is the expectation of that distribution. So the expectation of this with respect to the distribution Q theta. Well, that turns out to be a KL divergence between this numerator and this denominator. And you remember what KL divergence, like some of the properties of it?
Don't look in your slides.
So it's almost like a metric or like a distance function between distributions, in the sense that it's 0 if and only if the two distributions are equal. However, it's not symmetric, so it's not a metric in that way. Like metrics, these are functions that are symmetric in their inputs, but this is not. So it's not quite metric, but it's when in like information theory, this is a kind of function to compare the differences between two probability distributions. That pops up all the time whenever you have logs of ratios of distributions. So this is a thing where it's 0 if and only if these two things are the same. Now the same thing over here. Again, we have this Q theta, Q phi in the numerator. This is an expectation with respect to that distribution. So this is also a KL divergence. But this time, we're comparing not with the prior on our latent space, but with the the actual encoder network. Okay, so how is this good? It's just like more and more complicated, right? Well, the truth is that once you're expressing these things as KL divergences, like there's a lot of understanding here. Like you can think of these as terms that you're going to use to make in a loss you're going to make things go make these things go to zero so that these are more and more like each other. So that's good. In particular, like this was already noted, that we would want these two things to be similar to each other. That's like Q phi is actually trying to approximate phi theta. Although there are problems coming. There are dragons nearby. But here's what each one of these terms actually does mean. So, first of all, this term here. This term right here is how we're going to learn our p theta, this conditional here. Let me come back to that just a second. This term right here, this KL term, we're talking about it. Remember what we've done here. We've said this is a Gaussian. We just assumed it. A really nice Gaussian with the diagonal covariance matrix. And this actually is a Gaussian. It outputs the parameters of a Gaussian, and then we sample from it. So it's also a Gaussian. So it actually turns out that you can write this KL divergence, because it's two Gaussians, it has a really nice kind of closed analytic form, and with respect to these parameters, and it's easy to deal with. And what we want to do, right, we're not quite there yet. We're going to talk about what you want to do with each one of these terms, and why there's like a minus sign here and things like that. But remember, in the end, this is comparing these two distributions. And then this term right here, which actually seems so good, right? Like this seems exactly what we want to do. The trouble still is the fact that this is an intractable distribution. So actually, this thing right here, we still can't deal with. Like this is still a problem. This is some crazy integral. So like, remember this? We did this whole thing, kind of hoping to deal with the crazy integral, and we've done something. We've like made a bunch of terms pop out, but the truth is that this still, makes this intractable. So what do we do about it? Well, the truth is, what we do is just recognize that part of what it means to be a KL divergence is that this is greater than or equal to 0, always, no matter what you put in here. And it's 0 if and only if those two things are equal. So we at least know that this term right here is bounded below by 0. So it's a tight bound at 0. So this has our nice. This is just a log on the neural network output. No big deal. We can deal with that. This has a nice closed form. That's bad. We're going to basically ignore it, just knowing that it's always going to contribute something non-negative. And then what do we do with all of these things here? Well, we're just going to optimize this part of the loss here. So remember what we're trying to do. We're trying to maximize this. If we multiply this by -1, then we'd be trying to minimize this. But I haven't done that yet, right? We minimize negative log likelihood. We maximize log likelihood. So we're going to try to maximize that thing, which means we're going to maximize this, and just note that like whatever is here, it's going to contribute. It's going to contribute something positive. So we'll just ignore it and know that if whatever we're doing here is going to hopefully, if we can maximize that, then it'll it'll give enough signal to learn these things in such a way that we learn a useful we learn these useful encoder and decoder networks for our VAE.
So we're trying to maximize that, but wouldn't that mean we would also try to increase the other one?
Well, we just know that whatever that. So, yeah, that's not the case. Like if this ends up being positive, that's bad. Like the more positive this thing is here, the more different that is from like this thing here, right? So, yeah. So let's see. What am I trying to say here? Yeah. So what? Yeah. So we can't do anything about it, but we just know that as we maximize this, we. Hold on a second. I'm getting not confused that having said maximize and minimize so many times. Let me go to the next slide. Right. Yeah. It is just what I mean. Just what I'm saying. Sorry. So this becomes our loss function. So let's just focus on this for a second. This becomes our loss function. What we're trying to do is to maximize this with respect to our two sets of variables, the parameters for the decoder network and the parameters for the encoder network. And what happens if we maximize this? What happens with these two terms here?
That one gets as small as you can, the other one gets as big as you can.
Right. So as we maximize this right here, what this means is that we are doing a better and better job of reconstructing the data, right? As the probability of this, increases, what that represents is that the thing that we decode from Z, from our latent factors, is more and more likely to be from our data set. So that's enforcing like a good reconstruction. Notice that we're sampling over Z with respect to this Q phi. So this is also saying something. This is also like forcing something on Q phi as well. Like that needs to sample from the space in such a way that we do reconstruct as well. On this side, we have a negative value. So to maximize this, we actually, so this is negative. This is non-negative. So actually, multiply by -1 gives you a non-positive value. So to maximize, we actually need to make this as small as possible. This KL divergence as small as possible. What does that mean? Well, that means is you're actually taking this Q phi and you're forcing it to have the prior distribution that we picked for the latent space, which is usually this really simple Gaussian. So this term is saying, okay, learn to encode my data to this space, but do it in such a way that what we get in the end is this really nice simple Gaussian, and then reconstruct from there in such a way that I actually reconstruct from that space things in my data in my data space.
Wait,
Yeah.
Sorry for making you repeat, but
Yes, no.
could you clarify the second term, like the intuition behind it a little bit? I'm still a little unconvinced about it. Yeah. So why do we want the prior to equal to that for stereo distribution? What is the intuition behind it?
Why would we want this distribution to look like it's Gaussian here?
Yeah.
That's how we've chosen our latent space to be. We want a latent space to have, like in particular, we want the factors to be independent of each other. So we chose this distribution so that that's the case. And we like, this is a way of, like, what we choose for here is like a way of, it's a way of like putting our biases into how we want the factors to look.
Oh, so
Right, so like we could choose this to be anything, but we choose it to be Gaussian because like Gaussians are like have a lot of nice properties, and we choose it to have a diagonal covariance matrix. We usually choose it even to be isotropic, so that like this is basically just like a ball, you know, in whatever dimensional space it is, where the factors are independent of each other. And so when we say we want this thing to be to be as similar as possible to this, what we're saying is, as we encode from our data space to our latent space, we want it to be in such a way that this respects these the prior, or like these biases that we want on, like these preferences that we have for how that latent space should look. Again, like we chose a certain way, a certain set of those, just because of, like we chose this distribution because of like a couple things I've said a couple times now. But you could have chosen this to be anything, and so the problem would change in that now this thing, as it learns to encode, like you could choose this to be like uniform, for instance, like a uniform distribution, like in a fixed interval, and hope to get that to work. But the Gaussian works quite well. Okay. And then again, the whole point of this is just to make our reconstruction as faithful as possible. Remember, what's happening here is that this z is being sampled from q phi given the data itself. So it's way up there, which would be nice if it was repeated. But we're sampling z given the data point xi. Right, so like the image xi. And so we sampled it from there, and then when we reconstruct, we want that same data point to be as likely as possible given that z that we sampled. Right, so in that way we're like connecting the loop in the reconstruction. So the autoencoder would have you do this regression problem where you're literally bringing like each pixel value together. Here, this is a bit different. So saying, I'm given a data point, I sample some latent factor, and then I want to be able to, probabilistically recreate it. So, like the ideal case would be that this p is like very, very peaked around, around this data point, right? So, like, it's giving the highest probability to this data point, and then everything else around it, is low. So that you really only sample this. Does that make sense? So the same ideas that happen, like the same conceptual ideas are happening here. It's just formulated in a totally different way.
So for whatever z we have, we want to reconstruct an image we've already seen before in the training data.
Yeah, I mean that's how we're going to train this, right? That's exactly how we're going to train this. But there's now a probabilistic part of this, right? Where we're actually what we're truly doing is not reconstructing this. But we're generating the parameters for a Gaussian that we're going to sample this from, essentially.
But if we pick a z that we've never seen before, we should be able to reconstruct some kind of image that looks something like our.
Well, we remember the z's are never seen. The z's aren't part of our data.
Yeah.
The z's are latent; they're unobserved. So, like this whole process is allowing us to learn like a way of creating the z's. In a way that allows, for the like faithful reconstruction of our data, but also to like, have some strong prior on how those latents should behave.
But we pick some z out of random. If we randomly selected some z, then we should be able to create.
Well, when we're done with this, remember what we have is we can pick any z from our latent space and generate a sample from our data space, and that's the generative part, right? So it may, like I think kind of to your point, it could be that like we could well, there's going to be large. This is a continuous vector space, right? So like there are going to be lots of z's that we never saw in training. In fact, in general, any z that we sample here will not have been seen in training. But it will have learned to decode that to something. Hopefully, learn to decode that to something meaningful, a representative sample from our data space. Be honest, is anybody here just like super confused? Like, I don't know what's going on.
I mean, I understand the last equation, but the rest of it is.
Well, this is, I mean, hopefully at this point in your college career, you've learned that like what all this is like, 3 months of somebody banging their head against the wall.
Okay.
And then, and then they're like, oh yeah, and then here's how you do it, right? I mean, nobody looks at it like that and is like, oh, boom. Although after a while you kind of learn to play with things like that, I guess. But this is just like the most compact we have going from like the concept of we want to maximize a log likelihood to like the thing that we can actually maximize and like what those terms mean.
So we can just do stochastic gradient descent on this.
That's what we're going to do ascent.
Ascent.
Or we multiply by negative 1 and do descent. But yeah, that's exactly right. Like this is the thing that we're going to optimize. It's all differentiable, the whole thing. And it's often, this bound here is often called the elbow, the expected lower bound.
And we just hope the other term doesn't get big.
Yep, and we have no control over that. So we just sort of pretend like that never existed and just hope for the best. It's true. It's really true.
So has anyone studied what it kind of looks like when it gets big?
Yeah. I mean, yes, but most people just ignore it because either it works or it doesn't work. It actually works quite well for a lot of things. But again, this is like what we're doing is maximum likelihood, right? We're maximizing the likelihood function. So we're going to again be in a situation where we're going to get like blurry reconstructions often because we're going to be averaging over a lot of these peaked modes if our distribution is like that. Anyway, so I answered some of the questions of people who were willing to admit that they were confused. Who else is still confused here? Just be honest. It's okay. A couple people are still confused.
I'm confused, I just don't know what to ask you.
Here's the most important part. We have 10 minutes left, so we have to just kind of keep going. But the most important part really is we got to here, through some mysterious, pushing symbols around. We got to a point where we pushed the intractable parts into a place where we were like kind of okay, because the other parts that end up being tractable take care of the two things that we really cared about from the beginning. One is to be able to reconstruct, to have a way of expressing how we reconstruct, or having a loss that deals with the reconstruction of our initial data point as we go to a latent representation and back again. So that's what that even if you don't quite understand the math of that yet, like that's what this term is right here. It's like the x minus x hat loss term, and this one right here, this additional thing, is simply the fact that what we really want about our latent features is we want them to be independent. So pick this to be a distribution where the features of z are independent, and then this term is going to push those together so that our encoder basically has that property, or has something close to that property.
Since we're using like Gaussians for our priors, doesn't that make everything like blurry? Since we're trying to kind of a little bit blurry.
It's not necessarily blurry, but it does. But there is, So there's a dependence on the There's. Remember, you're learning the covariance structure here, so it doesn't have to be blurry. It can actually be quite sharp. But it might learn to be blurry because of just the way that the data is.
Because it seems like if you make it blurry, you can kind of cheat the loss function, because then it's kind of closer to.
Yeah, it's not really cheating, but it's a problem with the loss function itself.
Yeah.
Like the loss function allows that. And there's so many variations on variational autoencoders. That a lot of things I'm trying to do with those, with those kinds of issues. But this is just like the basic setup. Okay?
So can we, like, if we really wanted to, could we make P not like a direct delta function? So it's just a big spike in the middle?
P? You mean like the prior?
Yeah, the prior.
No, that would be terrible. Because what that would do is that would map all of your data points to a single latent point. That would be horrible. That's like the worst thing you could do. Does that make sense?
Yeah.
Yeah. Okay, we got to keep moving here. All right, putting it all together. That's the bound that we're going to try to maximize. So we have our encoder network takes us from input and not directly to output, or directly to the latent factors. It's going to predict the parameters of a distribution, and then we're going to sample from it. That term is making it so that what we end up getting is this nice Gaussian, for how we specify it for the latent space. So we get our Z, having sampled from that normal distribution with that predicted mean, that predicted covariance matrix. And then from there, we're going to decode it, but again, we're not going to decode directly to the reconstructed input data, but to this mean in this covariance matrix for Gaussian. And then we're going to sample from that, and this term right here is going to make it so that it's going to create the signal so that what we're trying to do is recreate this exact sample, despite the fact that we've introduced some noise as we're sampling from these distributions. And we haven't talked about it, and we won't talk about it just given the time, but you can backpropagate through this if you deal with the fact that there's some you can't truly backpropagate through this parameterized sampling here from this distribution. The way you deal with that is called the reparameterization trick, and again, it's this nice property of Gaussians where you can if you want to sample from any Gaussian, you can sample from a standard normal, and then you can transform that variable by multiplying by the covariance matrices in a certain way, and then adding the mean. So actually, what you do is you actually sample from a standard normal, which has no parameters that we're trying to learn, but then you transform that into a variable that comes from your Gaussian with these parameters, and the backpropagation works, which is awesome. Okay, so what do these things give you? So, for example, this could be compressing MNIST into 2 digits, into a latent space of dimension 2. Or this could just be like looking at 2 factors in a much higher dimensional space. But what it allows you to do now is to see what it is that these parameters are encoding. So let's say that we've done this. Our latent space is 2-dimensional. There's only 2 variables, Z1 and Z2 in our latent space. As we might pick 0, 0, maybe 0, 0. Like this thing right here, like this 8. And as we vary, Z1, the first entry in our latent space, up and down, keeping Z2 fixed, then you can see it starts to trace out starts to kind of work its way to be like a 3, then like a 2, like a 0. As you go down here, it's transitions to like a 9 and a 1. You can go the other direction. You can see how from here. You go this way with fix Z1, and as you change Z2, this is transitioning from an 8 through 9s to a 7, and 8s here through maybe going to a 1 or something like that. So this is what this thing learns to generate from any point in the latent space.
So Z2 is like the line-ness, and then the Z1 is like the loop-ness of numbers?
Could be, it could be. Sometimes it's hard to tell exactly what's going on here. But we don't have to do this with MNIST, we can do this with all kinds of data sets. So here's like the Stanford Faces data set. And you can see something really interesting happens here. So the Faces data set has something about like head pose in it, also like degree of smile and things like that. So they took a bunch of like very specific photos of people's faces where they like rotated a certain amount, like up and down, left and right. They had certain degrees of smiling and things like that. And this actually learns to like encode that actually fairly well. Again, these images are being generated by the variational autoencoder directly from the latent space. Again, two-dimensional here. So you can see really, really clearly that this Z2 does correspond to like, looking left to looking right, and this is Z1 from like scowling through smiling. And who knows what else you could learn from this data. Unfortunately, these kind of models are not very good at generating like very high resolution images. You can see that with CFAR. You can see that with these faces. Again, because this is like a maximum likelihood approach, and that tends to be averaging over the many modes. Like a face to be really high resolution, like all these pixels really need to be kind of arranged right and have sharp, transitions at edges and things like that. And this is not going to learn to do that in general. I mean, there's ways to kind of make it, but in general, it's not going to learn to do that. So, we need to find other techniques for doing that. But it is generating faces, which is kind of cool. And there's some other ideas here about denoising. I think we're out of time.
You can use it as a filter.
So you can, yeah. I mean, just real quick on the denoising is that you could treat this as a filter, right? You could add noise to your data, but then when you decode, don't decode to the image plus noise. Just decode to the supervise with the original image, and then you can learn to denoise things. Anyways, so this is the last slide, and we're done. What have we done today? We have learned something about what autoencoders are and variational autoencoders, like how they work, some of the math, well, all the math behind them, and like what those networks that you're learning are useful for. The real problems here is that we're not getting an explicit. We're only getting a bound for our data likelihood, so we don't really have we don't have this exact. We're not learning this exact representation of our data likelihood like we saw in RNN, pixel RNN, pixel CNN. And these samples are quite blurry and low quality compared to things that we're going to do on next time. These generative adversarial networks. All right, that's it for today. Sticking around for questions, and yeah.